Welcome to Section 9 of Neurology. In this section, I will be discussing the neurovasculature. The section is divided into two parts. In the first part of the section, I'll be providing an overview of the neurovasculature, and in the second part, I'll focus on examples and integrating the remaining material. Let's get started. This is figure 8.46 from your text, which provides a general overview of the neurovascular anatomy. I'm not going to read each structure to you, but it's very important for you to take some time to memorize the anatomy from this figure. We'll talk about these vessels in more detail as we go through practice questions, but recognize that each vessel in this image has clinical significance and has an important physiologic tie-in for step 1. Also, before we dive deeper into the anatomy, I'd like to mention that once the vasculature reaches the brain, its composition slightly changes into what's known as the blood-brain barrier. For step 1, you need to know that the blood-brain barrier is composed of three things: the endothelial cells, astrocytes, and pericytes. Okay, now let's zoom up on this region here. This is figure 8.47 from your text, which shows a close-up view of the circle of Willis. Again, I'm not going to read the labels from this image, but you will need to take some time to commit this to memory. Hopefully, as we go through some questions, the anatomy will become solidified and these images will become easy to recall. This is figure 8.48 from your text, which shows the important neurovascular territories. I recognize that the entirety of this figure is difficult to see on a single slide, so we'll break this figure up into 5 separate slides. However, this figure should be very clear in your text, which should allow you to easily review the material. Notice that only the vascular territories of 3 arteries are shown in this figure: the posterior cerebral artery, the middle cerebral artery, and the anterior cerebral artery. As we go through each component of this figure, I won't read the labels to you, but hopefully you'll pause the video and take some time to memorize what arteries supply the different territories of the brain. This is a lateral view of the neurovascular territories. This is an inferior view of the neurovascular territories. This is a mid-sagittal view of the neurovascular territories. This is a transverse view of the neurovascular territories. This is a coronal view of the neurovascular territories, which is probably the most important view to be familiar with. This is because when we combine this image with the homunculus, we can deduce many of the symptoms that a patient should experience if one of the vessels feeding these territories was occluded. Again, this is figure 8.6, which shows the homunculus. Remember, this image represents both the primary motor and primary sensory cortices. From the last slide, we know that this region here is fed by the anterior cerebral artery, or ACA. So you can imagine if the patient had a stroke of the ACA, then he or she would experience paralysis and sensory deficits of the leg. Because the motor and sensory pathways decussate, we should be able to deduce that occlusion of the left anterior cerebral artery would result in paralysis and sensory deficits of the right lower limb. Again, from the last slide, we know that this region here is supplied by the middle cerebral artery, or MCA. This means occlusion of the MCA would result in contralateral paralysis and sensory deficits of the upper limb, face, and mouth. The posterior cerebral artery, or PCA, doesn't supply blood to the primary motor and sensory cortices, so the homunculus can't help us here. However, the PCA supplies blood to the occipital cortex, which is responsible for vision, so occlusion of the PCA should result in visual deficits, which is discussed more in Section 8. Recall from Section 8 that the MCA supplies blood to the macula of the eyes, so occlusion of the PCA would result in visual deficits with sparing of the macula. This is figure 8.49, which provides a coronal view of the lenticulostriate arteries. Notice that the lenticulostriate arteries are branches of the middle cerebral arteries. So we have the right middle cerebral artery and the left middle cerebral artery. It's important to know that the lenticulostriate arteries supply blood to the internal capsule and basal ganglia. We can see the internal capsule right here, as well as the basal ganglia. We have the putamen, the globus pallidus, the caudate nucleus, and the thalamus. Knowing this, we can deduce the symptoms a patient may have if these arteries are damaged. Damage to the internal capsule would result in contralateral paralysis and sensory deficits. This is because the corticospinal tract and the thalamocortical tracts pass through the internal capsule. Damage to the basal ganglia would result in movement abnormalities, which are highly variable depending on the region that's damaged. For more information on the details of the basal ganglia, refer to section 6. For step 1, it's important to know that the lenticulostriate arteries are commonly affected in patients with chronic hypertension, which we'll talk about more later. This is table 8.4 from your text, which provides an overview of the effects of strokes. We just discussed the anterior cerebral artery, the middle cerebral artery, the lenticulostriate artery, and the posterior cerebral artery. So I'm not going to cover that again, but feel free to pause the video and review that information from the table. The basilar artery is a major vessel that supplies blood to the midbrain, pons, and medulla. So all of these regions are damaged during an occlusion. Because there are so many areas of the brainstem that are damaged during a basilar artery occlusion, I find it most helpful to remember the structures that aren't damaged. These include the oculomotor nerve, so cranial nerve 3, and the reticular activating system. Recall that cranial nerve 3 allows the eyes to move vertically, so vertical eye movement is intact. Cranial nerve 3 also innervates the levator palpebrae superioris muscle, which is responsible for opening the eye. Because this muscle is under conscious control, patients can relax the muscle, causing the eye to close. This is why patients with a basilar artery occlusion can blink, so blinking is intact. For step 1, it's important to know that the reticular activating system includes the reticular formation and the tegmentum. Let's pull up some images to make this a little clearer. From figure 8.46, we can see the basilar artery is right here. Notice how the basilar artery is in the midline of the brainstem and supplies blood to the medulla, pons, and the midbrain. This is figure 8.16, which is a transverse section of the midbrain. This is anterior, and this is posterior. From the last image, we know that the basilar artery is about right here. The branches of the basilar artery dive deep into the brainstem, so much of the anatomy is affected. However, the oculomotor nerve, right here, is one of the deeper structures of the midbrain and is typically not damaged during occlusion of the basilar artery. This is why patients can blink and move their eyes vertically. The reticular formation is a group of many nuclei throughout the brainstem, so it can't be easily identified on one image like this. The tegmentum is also a general area within the brainstem, but on this section of the midbrain, it's located throughout this region of the white matter here. Notice how it's a general area between the cerebral aqueduct and the substantia nigra. Both the reticular formation and the tegmentum are involved in sleep-wake cycles and are important in preserving consciousness. Because these structures are so ubiquitous, they're typically somewhat preserved during an occlusion of the basilar artery, which explains why the patient can have preserved consciousness. Okay, moving on to the anterior inferior cerebellar artery. Occlusion of this artery is also called lateral pontine syndrome. Because the lateral pons is damaged, we'd expect all the structures in this region to be affected. Let's pull up some images to more clearly see what structures are damaged. From figure 8.46, we can see that the anterior inferior cerebellar artery is right here. Notice how this artery wraps around the lateral aspect of the pons. This is why when it's occluded, the lateral pons becomes ischemic, hence the name lateral pontine syndrome. From figure 8.18, which shows a transverse section of the pons, we can more clearly identify the structures that would be damaged in lateral pontine syndrome. This is anterior, and this is posterior. So again, the anterior inferior cerebellar artery supplies blood to the lateral pons, or approximately this region here. For this syndrome, it's most important to remember that the facial nucleus and the solitary nucleus are damaged. Damage to the motor aspect of the facial nucleus will result in total ipsilateral facial paralysis. Recall that the solitary nucleus contains sensory information from cranial nerves 7, 9, and 10. Knocking out the sensory aspect of the facial nerve would result in taste deficits from the ipsilateral anterior 2/3 of the tongue. Knocking out sensory aspects of cranial nerves 9 and 10 would result in more vague symptoms such as abnormalities associated with the monitoring of the baroreceptor and chemoreceptor reflexes. So again, facial paralysis and taste deficits from the anterior 2/3 of the tongue are symptoms unique to lateral pontine syndrome. Also notice several other structures in the lateral pons, including the vestibular nuclei, the spinothalamic tract, and the middle cerebellar peduncle. The inferior cerebellar peduncle can also be damaged, which can't be seen on this image, but it's directly inferior to the middle cerebellar peduncle. In order to see this, we'd have to take a cross-section of the caudal pons. It's also worthwhile mentioning that the lateral tegmentum, or this general area in the white matter here, can be damaged, which contains descending fibers from the hypothalamospinal tract. Recall that this tract contains important sympathetic information that will return to the face, so damage to this region can result in Horner syndrome. Damage to each of these structures explains the other symptoms associated with lateral pontine syndrome, which you can review from table 8.4 if you'd like. However, many of the symptoms seen in this syndrome are identical to lateral medullary syndrome, so it's important to know that damage to the facial nucleus and the solitary nucleus are unique to this syndrome. Okay, let's move on to lateral medullary syndrome. The posterior inferior cerebellar artery, or pica, is an important vascular contributor to the lateral medulla. For this reason, occlusion of this artery is also called lateral medullary syndrome. It's important to know that the pica is a direct branch of the vertebral artery, so occlusion of the vertebral artery can also result in lateral medullary syndrome. Because the lateral medulla is damaged, we'd expect all the structures in this region to be affected. Let's pull up some of the figures to more clearly see what structures are damaged. From figure 8.46, we can see that the posterior inferior cerebellar artery, or pica, is right here. Notice how this artery wraps around the lateral aspect of the medulla. Also notice that the pica is a direct branch of the vertebral artery. This is why when the vertebral artery or the pica are occluded, the lateral medulla becomes ischemic. From figure 8.20, which shows a transverse section of the medulla, we can more clearly identify the structures that would be damaged in lateral medullary syndrome. Again, this is anterior and this is posterior. The pica supplies blood to the lateral medulla, or approximately this region here. For this syndrome, it's most important to remember that the nucleus ambiguus is damaged. Recall that the nucleus ambiguus contains motor information from cranial nerves 9 and 10. From section 3, recall that cranial nerves 9 and 10 provide motor output to the pharynx and larynx, so damage to these structures would result in dysphagia, and dysphonia, or difficulty eating and difficulty speaking. Also notice several other structures in the lateral medulla, including the vestibular nuclei, the spinothalamic tract, and the inferior cerebellar peduncle. Also note that the lateral tegmentum, or this general area here within the white matter, can also be damaged, resulting in Horner syndrome. Damage to these structures explains the other symptoms associated with lateral medullary syndrome, which you can review from Table 8.4 if you'd like. However, many of the symptoms seen in this syndrome are identical to lateral pontine syndrome, so it's most important to know that damage to the nucleus ambiguus is unique to this syndrome. Okay, the last artery to be familiar with is the anterior spinal artery. Let's pull up some images to more clearly see what structures are damaged. From figure 8.46, we can see that the anterior spinal artery, or ASA, is right here. Notice from this image and from the name of the vessel how this artery supplies blood to the anterior aspect of the spinal cord. However, it's also important to know that branches from the ASA, called paramedian branches, supply blood to the medial aspect of the medulla. Let's look at a cross-section of the medulla to see what structures are affected. On this slide we have figure 8.20, which shows a transverse section of the medulla. It's important to know that the paramedian branches of the ASA supply blood to approximately this region right here. Notice how these arteries supply the medial aspect of the medulla, and the most medial arteries extend relatively deep into the medulla, as we can see right here. As we can see, the hypoglossal nucleus is right here. And because this nucleus is so medial and deep, it can become ischemic during occlusion of the ASA or the paramedian branches of the ASA. Also notice how the medial lemniscus, right here, and the corticospinal tract, right here, are both medial and receive blood directly from the paramedian branches of the ASA. Recall from Table 8.4 that these are the three structures that are damaged during an occlusion of the ASA. Also remember from Section 3 on cranial nerves that damage to the hypoglossal nucleus results in tongue deviation to the ipsilateral side. Recall from Section 2 on spinal tracts, figure 8.13, which outlines the pathway for the dorsal column. As we can see from this image, the dorsal columns ascend through the medial lemniscus and are responsible for vibration and proprioception. So damage to the medial lemniscus in an ASA stroke would result in contralateral loss of vibration and proprioception. Note that loss of sensation is contralateral because the pathway decussates before the medial lemniscus, as we can see right here. Decussation. Also recall from Section 2 on spinal tracts, figure 8.15, which outlines the pathway for the corticospinal tract. As we can see from this image, the corticospinal tract descends through the anterior pyramids and is responsible for movement. So damage to the anterior medulla in an ASA stroke would result in contralateral paralysis. Note that the paralysis is contralateral because we're assuming the pathway is damaged at this region. Okay, before we move on to aneurysms, I'd like to briefly mention another type of lesion associated with the ASA. This is figure 8.9, which shows a cross-section of the spinal cord. After the ASA descends past the medulla, it supplies blood to approximately this region here. Notice how this vascular territory supplies the anterior and lateral aspects of the spinal cord, but spares the dorsal columns. This means if the blood supply is compromised, the patient will present with bilateral paralysis due to disruption of the corticospinal tracts, bilateral loss of pain and temperature due to disruption of the spinothalamic tracts, and intact proprioception and vibration due to sparing of the dorsal columns. For step 1, you need to know that there are several anastomoses between the ASA and other arteries that supplies collateral circulation to this region. This is important because it means an occlusion of one of these vessels is less likely to cause significant ischemia to the spinal cord. So if you ever get a question about damage to the spinal cord with sparing of the dorsal columns, it will likely be in the context of hypoperfusion to the ASA and its collateral circulation. Okay, let's move on to aneurysms. An aneurysm is simply a balloon-like dilatation of an artery. There are two types of aneurysms you need to be familiar with for step 1. Saccular or Berry aneurysms and Charcot-Bouchard microaneurysms. Saccular aneurysms are relatively large and are commonly associated with connective tissue disorders such as Ehlers-Danlos syndrome, smoking, and age. It's important to know that these aneurysms can either rupture or can compress nearby structures. If they rupture, they can cause a subarachnoid hemorrhage and/or ischemia to the nearby region. If they compress nearby structures, the patient may have clinically significant symptoms, but this depends on the location of the aneurysm. On the other hand, Charcot-Bouchard microaneurysms are microscopic dilatations of arteries that occurs as a result of chronic hypertension. It's important to know that this type of aneurysm most commonly occurs in the lenticulostriate arteries. This is table 8.5 from your text, which provides a list of clinically relevant aneurysms and the associated lesion area and symptoms. An aneurysm of the MCA or the lenticulostriate arteries are essentially identical to a stroke in these regions, which is clearly explained in table 8.4, so I'm not going to repeat this information. For step 1, you need to know that rupture of an aneurysm originating from the anterior communicating artery, or ACOM, can result in ischemia to the anterior cerebral artery, or ACA distribution. Again, we already discussed a stroke of the ACA in table 8.4, so I'm not going to repeat that. You also need to know that a saccular aneurysm originating from the ACOM can compress the optic chiasm, resulting in bitemporal hemianopia. Let's pull up an image so you can see what I'm talking about. From figure 8.47, we can clearly see that an aneurysm originating from this region here could compress the optic chiasm, resulting in bitemporal hemianopia. If you're unfamiliar with bitemporal hemianopia, I recommend watching the section on ophthalmology. Of all the aneurysms to be familiar with for step 1, I think the posterior communicating artery, or PCOM, is the most important. This is because an aneurysm originating from the PCOM can compress the oculomotor nerve, or cranial nerve 3. It's important to know that the oculomotor nerve sends parasympathetic information to the eye through the superficial axonal fibers and somatic information to the eye through deep axonal fibers. So superficial fibers contain parasympathetic information, whereas deep axonal fibers contain somatic information. This means the size of the aneurysm and degree to which it compresses the oculomotor nerve determines the patient's symptoms. Compression of the superficial parasympathetic fibers of cranial nerve 3 results in mydriasis and ptosis, and compression of the deep somatic fibers of cranial nerve 3 can result in paralysis of the corresponding ocular muscles. From figure 8.47, we can clearly see the posterior communicating artery right here. Recall that the oculomotor nerve passes between the superior cerebellar artery and posterior cerebral artery as it projects anterior like this. This means that an aneurysm originating from the PCOM right here could compress the oculomotor nerve, resulting in the symptoms we just discussed.